Hey guys, welcome back to the second video in our lecture series. This one's titled Orthonormal Functions. Is that really a thing? Keeping with our analogy with vectors, we can define the norm of a vector as the square root of its inner product with itself. For any vector in three-dimensional space, this will give the length of the vector. And dividing the vector by this magnitude gives us a vector of length 1, and so we can call this vector normalized. Since we've already defined the inner product of two functions, it's easy now to define the norm of a function as the square root of its inner product with itself. Then we can similarly divide the original function by the magnitude obtained by taking the norm of the function and normalize the function. We can then define a set of orthogonal functions, all which have been normalized as an orthonormal set of functions.
In the last example, we showed that this set contains 1 and this infinite series of cosine functions is orthogonal on the interval from negative p to p. Now let's normalize it. We begin by taking the inner product of one of these cosine functions, order n, with itself, giving this integral with a cosine squared term. In order to evaluate this, we can turn to this trig identity or double angle formula. If a is any real number, then cosine squared of ax is equal to 1/2 of cosine of double this angle plus 1. Applying this trig identity, we arrive at an integral which we can easily calculate directly. Similarly, the last time, plugging p or negative p into this sine function, the p's cancel out and the sine goes to 0. We have this extra x term, so evaluating this gives us p. Now this holds for any n in the natural numbers except for 0, because we can't let n equal 0 due to the n in the denominator here. Again, so the norm of cosine n pi over px is then equal to the square root of p for all n in the natural numbers not equal to 0. When n is equal to 0, it gives us this 1, the function equal to 1. We can calculate its norm directly as well. See that the inner product of 1 with itself is equal to 2p, so that the norm is equal to the square root of 2p. Okay, so we have therefore calculated the norm of each of the functions in our infinite orthogonal set of functions, which leads us to the claim that this set of each of the functions divided by their norm is orthonormal.
Thanks for learning math.